Now we're going to illustrate the Gram-Schmidt process with a set of three vectors. So let this, and this is a basis, these three vectors are linearly independent, and we can establish that without too much trouble. These three vectors are linearly independent, many ways to show that. And we're going to call these three vectors respectively v1, v2, v3. Now, we're going to rearrange, we're going to modify this set of vectors so that it's orthogonal. So we have an orthogonal set that spans the same space as these three. Of course, the space in this case would be all of R3, right? But this will work even if you have a span of a subspace of some larger vector space, some vector space of higher dimension. Okay, so these aren't orthogonal. Dot product of this with this isn't zero. Dot product of this with this isn't zero. Dot product of this with this isn't zero. Nothing's orthogonal to anything else. We want an orthogonal basis, and we can use this basis to develop one. Okay, so what we're going to do is we're going to let our new basis be and I've had a little trouble with my shoulder. Don't know if I can write up this high. I'll go left-handed. It's not going to be pretty, but so we want to get an orthogonal basis and that might be a little hard to read, but and I know it's a little slow. I hate to take your time here, but W1, W2, W3. Okay, so to get our orthogonal basis, I'm just going to let W1 equal the first vector, which is the 1, 1, 0 vector. Okay, so that's a good start for an orthogonal basis. We don't care what orthogonal basis we get. We'll take any orthogonal basis. So W1 is your V1. We're going to let W2 be V2 minus the projection onto W1 of V2. Picture that. Here's V1, which is now also called W1. Here's V2. Here's our projection of V2 onto W1. And we subtract that from V2, and we get this because, of course, the projection plus this equals V2. Therefore, this equals V2 minus the projection, which is what we've written here. And we just saw that, and we've seen that now 2 or 3 times. Okay. So now we've got a W2, and this vector is perpendicular or orthogonal to W1. Perpendicular in R3, but I'll use the orthogonal term. So we just got, now we have 2 vectors. We got our W1 and our W2. So now all we have to do is get our W3. Okay, well, let me just say that what we're really doing when we subtract the projection from W2, what is the projection? The projection is the component of V2 in the direction of W1. Okay, this is the component of V2 in this direction. V2 is equal to this component plus this component. This component is the component perpendicular to W1. So in order to get a vector perpendicular to W1 from our vector V2, we simply subtract the parallel component because the parallel component plus the perpendicular component add up to V2. So the perpendicular component, which is perpendicular to W1, is equal to V2 minus the component of V2 parallel to W1. Okay? Well, we're going to actually do the same thing with V3. We're going to subtract the component of V3 in the direction of W1, and then from that, and that's going to give us a vector that's perpendicular or orthogonal to W1, right? So we could even say that this is orthogonal to W1, and then we subtract the projection of this vector, we subtract the component of a same vector relative to W2, so now it's also perpendicular to W2. And I just thought of something that I'm not sure I like. Anyhow, there we have it. Okay. Now, and if the thing I just thought of that I don't like turns out to be really something I don't like, everything I'm doing here is a little bit suspect. Pretty sure this is right, though. I mean, there's something I need to prove to myself, and we need to do that as a mathematician or as somebody who's using a lot of mathematics. You always question what you're doing. So even though I'm pretty sure of this, I'm questioning it right now. And I'm going to have to prove to myself something that I'm no longer able to quickly prove in my head, even though I think everything is okay here. Okay, well, so my point now is when I subtract the projection of V3 on W1 from V3, I eliminate the component of V3 that's parallel to W1. And then I eliminate the component of V3 that's parallel to W2. And the question I just had, which is really kind of a stupid question, has been answered. Because W1 and W2 are parallel, my concern is no longer there. Just a little aside. You can ignore that. Okay, so again, we subtract the component of V3 in the direction of W1, then from that, from V3, and then we subtract also the component of V3 in the direction of W2, and now we're left with whatever remains of V3 that's not in the direction of either W1 or W2, so it's orthogonal to W1 and W2. So that W3 has to be orthogonal to both W1 and W2. Now the procedure is pretty straightforward. If we had a higher dimensional space, because we could let V1, V2, and V3 be just any three vectors, because I haven't ever used these three vectors yet. I'm going to work it out with these three vectors. Okay. If we're in 8-dimensional space, I could have three vectors, linearly independent vectors in 8-dimensional space. They'll span a subspace, a 3-dimensional subspace of 8-dimensional space. They're not necessarily orthogonal to one another. They probably aren't if I've just got three random vectors, but they are linearly independent. So I do this, and it all works out. Now what if I had four vectors in 8-dimensional space or 18-dimensional space, whatever, in a higher dimensional space? How would I continue the process? Well, if I had a W4, I mean, if I had W1, W2, and W3, and if I had a V4 that was linearly independent of the others, I could subtract the projections of V4 onto W1, and then onto W2, and then the projection onto W3. The calculation would look just like this, but I'd have to subtract another projection. Every time I get another W vector, I take the next V vector and subtract all the projections on the W vectors, and I've got something perpendicular to all those vectors. Now I'm just kind of waving my hands here. I haven't proved any of this, but it's valid. Okay. Okay, anyhow, back to the original example. This W1, W2, W3 will then be an orthogonal set spanning the same space as V1, V2, V3, whatever your space. Now, for the specific three vectors I have here, let's go ahead and do this. Okay, W1 equals V1, and of course that's the vector 1, 1, 0. And checking my time, we can get through this pretty quickly, so I'm going to continue this. The projection of V2 then onto W1 is what? Well, we developed this last time. Remember that because of all kinds of things, the magnitude of the projection, except maybe with a minus sign, depending whether the projections are the same or opposite direction to W1, but the magnitude, plus or minus, of this projection is V2.W1 divided by the magnitude of W1. Remember, that just comes back to the right triangle with the theta and the relationship between the dot product and the cosine of theta. So review that if you don't have that down, but that's something you really want to know. We take that and we multiply it by the unit vector in the direction of W. And that gives us a vector in the of W1. And that gives us a vector in the direction of W1 with this magnitude, and that's exactly what we mean by the projection. Okay, so just calculating it, I just do the dot product of V2 with W1, W1 being the same as V1, and then I divide by the magnitude of W1. It's easy to verify the magnitude of this vector, square root of the dot product with itself, or Pythagorean theorem if you like it right now, is square root of 2. And then we multiply that by the vector 1, 1, 0 divided by square root of 2, the vector W1 divided by its magnitude. And we get 1, 1, 0 over 2, which is 1/2, 1/2, 0. So there's our vector W2. And I don't know that I actually specified that that's W2, but it is. So, no, that's not W2 at all. Okay. We don't have W2 yet. This is the projection of V2 on W1. We have to subtract that projection from V2. So that's what we do here, and that's our W2, V2 minus the projection onto W1 of V2. And W1 is 0, 1, 1. The projection is 1/2, 1/2, 0. We subtract it, and we get the vector negative 1/2, 1/2, 1, which we have right here. And we can verify that this dot product with W1 is 0. Dot product of this with this, well, you get negative 1/2 plus 1/2, and that's 0. Then W3. We do the same thing, except now we have two orthogonal vectors. And we're going to have to subtract the projection of V3 onto each of those vectors from the V3 vector in order to get our W3 vector. Now, I didn't actually do that. I just left that as something for you to complete, and then to verify that this is W3 is perpendicular to W1 and W2. And what I've written here, I've already talked about, so I think we're in good shape here.